And I will hand it over to Dr. Rachel Smith, and she will introduce our guest speaker for today's session.
Thank you. Thank you. Hi, everyone. Thanks for coming to this, what I know will be a great talk. And I'm excited to introduce my friend and colleague, Dr. Pierre Haenecour. And he's going to tell us about NASA's OSIRIS-REx mission, which is a sample return from an asteroid. So that is so super cool. And just as an introduction, since 2019, Pierre has been an assistant professor at the Lunar and Planetary Laboratory at the University of Arizona. And his research focuses on the building blocks and early history of the solar systems, of the solar system. And so asteroids are these relics of our history. So this is going to be such a cool mission, and I'm sure an exciting talk. He's interested in the origin of life, and he explores circumstellar and interstellar dust grains and organic molecules. And he's also looks at meteorites and little teeny tiny pieces of meteorites called micrometeorites, as well as interplanetary dust particles. He got his PhD at Washington University in St. Louis and was a postdoc at University of Arizona from 2017 to 2019 before becoming a professor. And he is a good friend, and I'm so excited that he could come virtually and hopefully in person sometime in the near future when we're all back to normal. So thank you, Pierre, for coming, and I'll leave it to you to tell us.
Thank you very much, Rachel. Let me share my screen. Okay. Thank you very much for inviting me. I'm really excited to be able to share some of the work that the mission has been working on in the past few years, and especially in the past few months with the sample collection, and then introduce you some of the work that I'm doing at the moment and that in anticipation for the mission and what we are planning for when the sample will actually return to the Earth. So as some of you might be aware of, Carl Sagan had this really famous quote that we are made of star stuff. And what he meant by that is that all the elements in our body, the large majority of them, were formed originally in previous generation of stars. So stars before our solar system even formed. And when I talk about, if you've seen in my title, when I talk about volatiles in particular, we talk about those really light elements such as oxygen, hydrogen, carbon, or nitrogen. Then all those elements compose up to over 95% of our body and a large majority of the composition of even of the Earth in general. And so one of the work that I've been really interested in is trying to understand how those elements and more generally our life. So if you look at most life on Earth is basically based on oxygen, on all those elements. So life is based carbon-based, but also water-based. So there's a lot of oxygen, hydrogen, and carbon. And so what we have been looking for is trying to understand how those elements were actually delivered or actually were contributed to the Earth and led to the development of life on our planet. So one of the things that we are looking for is because during the Earth's formation, a lot of the original signature were lost through extensive processes. And so here it's a mosaic that's shown at NASA Ames, at one of the NASA center. And I really like that illustration because it basically shows how complicated the story is, where a lot of processes happen on the surface of the Earth, but as well in space. And so one of the big aspects of the work that I'm doing is trying to reconcile all this history. And so a lot of the original history of the Earth, it was lost by billions of years of processes on the surface of the Earth. So if you ever seen a volcano in Hawaii, for example, all that process melting and the reprocessing of material made us that we lost a lot of those signatures. So the way we can actually investigate the origin of life on our planet is by looking at other bodies in our solar system, and in particular, looking at the leftovers of solar system formation. What I mean by leftovers is our planets in our solar system and the Earth were formed by collision of bodies and accretion of ancient material together that basically accreted in this really large disk of dust and gas, forming all the planets that you can see in our solar system. And if you attended the previous talk by Rachel, she basically drove you around showing you all the different planets throughout our solar system. And so you've seen that all the diversity of planets, and then there is those two main regions in our solar system where there is those old undifferentiated body. And what I mean by undifferentiated is like, unlike the Earth, they didn't experience differentiating into a crust, mantle, and core. And so basically all those leftovers bodies, which are asteroids and comets that we found within our solar system, are literally leftover material that didn't were included in the planet. So they are literally, if you've seen fossils on the Earth to understand, in paleontology, for example, they are literally fossils of remnants of the early solar system. And here I show you the general structure of how we think the asteroids and comets were structured in the really early solar system. So while the planets were actually forming, there was this region in the inner solar system where asteroid was, which is the asteroid belt that's between Mars and Jupiter. And then there is this outer region where there is all the comets. And one of the big distinctions between those two regions is what we call, it's one particular region which is called the snow line, which is the limit, the distance from the sun where actual solid ice can actually condense. And so basically the difference between asteroids and comets is that asteroids are usually in a region that's too warm to be really ice rich. And so we have a high concentration of ice, while comets are really enriched in ice. So they are this, you can imagine comets are like a snowball where composed of dust and ice mixed together. And so one of the big work that we have been investigating is try to retrace how water and organics, in particular some key organic compounds that were the starting material from which life evolved, were delivered to the Earth, so through comets or asteroids. And so we have been focusing, a lot of my work have been focusing on trying to retrace how we can use sample in the lab, and in particular meteorite, and we're going to show you in a minute, to try to investigate how asteroid might have seeded the Earth with key bioessential elements that led to water and life on Earth. So here I'll show you the overall solar system as it is now. And so you can see the asteroid belts between Mars and Jupiter, and then comets. And so basically what the work I'm doing, as I mentioned, will be retracing those bioessential elements as a source of those of life on Earth. And one of the key things that we can do is, because asteroids are so far away between Mars and Jupiter, and we can get little information from them just from remote sensing observation, because most remote sensing observation give us information on, we can get images, we can get spectral information, so just by looking at the light emitted by those bodies, but we can't get really in situ information on those bodies. But the only way we can get those is through fragment of those asteroids that get destabilized and are brought to cross the Earth's orbit, and some of them actually enter the Earth's atmosphere as meteorites. And here I show you an example of a NASA image of the day. That was it's a really nice image showing one of those fireballs. So we call it fireball. If you ever look at the sky at night, it's very you can see them relatively often, where you see those really beautiful. And if you've seen the really famous one that was the most recent was Chelyabinsk in Russia, that was captured in a lot of videos, where you see the fireball crossing the sky and landing on the Earth. And so the remnant rock that you can actually find on the surface is what we call a meteorite. And here the picture at the bottom of the slide, it's a meteorite with these black rocks sitting on the surface of the ice in Antarctica. And so NASA in particular goes every year collecting meteorite in Antarctica. And the reason why we go to Antarctica is because it's not because there is more meteorite, but it's just because there is so much ice and so little rocks on the surface in Antarctica that it's easy to find a black rocks on the surface. And so the probability of finding, it's just the probability of finding a meteorite is much higher. So, and then we can bring that meteorite in the lab and do analysis in the lab. Some of the analysis that I do in the labs is working, as Rachel mentioned, is working on two key samples. So I work on meteorites, as I showed you in the previous slide, but I also works on those small meteorites that were called micrometeorites. And so as you can see here, micrometeorites, they are very small. They're on the order of about 200 microns. So if you want a scale for reference, the diameter of one of your hair is generally about 75 microns. So it's just barely bigger than one of a human hair. So it's really, really small. So we need really high resolution techniques in the lab to be able to even study them in detail. And so the name of the instrument don't really matter, so I'm not going to go in detail about the actual technique. I just wanted to show you the general flow of measurement. So we use a series of really high resolution technique to try to get information on those samples and try to get as much information without destroying materials. So because those samples are so precious, you want to extract as much information as possible without while doing as little damage as possible. And so as you can see here, it's just a general image of the micrometeorite when after it was collected in the ice. So the way micrometeorites are typically collected, they basically get a really large amount of snow from Antarctica and then melt it slowly in the lab, and then collect the dust, small dust grain remaining in the snow. And so a lot of those, up to about 80% of those particles, are actual micrometeorite. And fun fact, you can actually, if you ever collected rainwater, even in your house, you can actually find micrometeorites in the rainwater, because there is tons of material that basically fall onto the Earth through the Earth's atmosphere every day. So there's a lot of micrometeorite that actually fall through the sky every day. And so then what we did is we pressed those micrometeorites into a gold. So here it shows you on the lower left side, show you the micrometeorite pressed into gold to basically have a flat surface. So it allows us to do really in situ measurement in the lab. And I show you an image of that particular micrometeorite. I highlighted in red. So it's just an overview image of the actual micrometeorite pressed into gold. So now the surface is actually flat. And we can look for those organic compound or original materials that basically organic molecules. And so Rachel mentioned it in the previous talks, if you had the chance to go to, where it's those some meteorites and macrometeorite and asteroids, their parent body asteroid, have those key organic compounds such as amino acid, for example, that we can study and retrace to try to understand how those molecules evolved and were created and then evolved to then land on Earth to basically develop much more complex compounds that leading to the origin, leading to actual living organism. The way we do it is in situ. So here you can see we use imaging, and one of the key things we use for retracing the origin of a material is what we call isotopes, which are different form of the same elements, that have different atomic mass. And so when we basically map those isotopes in situ, and so here you can see the one example of a map. So it's a nitrogen isotope, so nitrogen 14:15 ratio. So you're just comparing the ratio of that particular isotopes pixel by pixel. So it gives you basically an image. So each pixel has a specific isotopic ratio, and you can see in that image there is this region that's really blue red. That means that it has this enrichment we call it nitrogen 15. So it's much more enriched nitrogen 15 than anything on the Earth. And I'm going to show you in the next slide what I mean by enrichment. So when we look for fingerprinting, literally, it's like if you think about it as like a crime scene or like investigation where you try to retrace the origin and finding the key to solve an issue. Isotopes are basically that key where you can actually retrace the origin of a compound by just comparing this isotopic composition to other material. And so here I show you some of the key nitrogen isotopic composition throughout the solar system. So the reference material is the Earth, in particular the Earth's atmosphere. So that's why it's N2, so for the nitrogen in the Earth's atmosphere. And so that's how the composition, the ratio of the Earth in the Earth's atmosphere, it's listed here. Then the sun. So because the sun is over 99% of the material in our solar system. So it's really its isotopic composition is a key to understanding the rest of the solar system. So we can see that the composition of the sun was measured thanks to the NASA Genesis mission that measured the solar wind. So it measured basically the wind coming out of the sun. So it basically allows us to get a measurement of its nitrogen isotopic composition. Jupiter, that's mostly that's the largest gas giant, and basically shows that because there is so much nitrogen gas that is basically has a very similar isotopic composition as the sun, which makes sense because both are the two biggest sources of nitrogen in the solar system. And then we can also compare them to comets and asteroids, so the body that basically we think were the two potential key delivery of volatiles, so those light elements to the Earth. And so when we compare them, you can basically see that we see much different isotopic composition between asteroids, between comets. And so basically we try to retrace them as best as we can by basically measuring as many samples and many meteorites as we can. And then the last one that I included for reference, and I'm going to come back to it when I talk about the origin of those organics, is what we call interstellar molecular cloud, which is those really large clouds of dust and gas from which the solar system forms. So it's basically include the cloud collapse, and then there was material concentrating, forming a central star, and then you have a disk of material around it that basically allow planets to accrete together, so forming the solar system. So it's basically similar to those interstellar molecular clouds, that's basically those really large clouds from which the solar system likely also formed. So one of the key investigations then we do is basically try to understand the actual composition of that particular region. So that particular, we call it a hotspot because it's very different in isotopic composition from the rest of the solar system. And so what we did is we literally cut a cross section. So we extract a lamella of material from the sample in situ. And so here I show you the direction of the lamella, and I'm going to show you a picture of the lamella in the next slide, but just to show you the orientation of how it goes. So basically, instead of just seeing the surface, now we go in cross section inside of the sample. And so here I show you the cross section. So basically, you can see the arrow in red show you where the hotspot was, and so it shows you that there is this particular region on the top, and is the dark on that image show you that it's carbon rich, and so it shows that it has this we call it nanoglobules, which is basically just a bubble of carbon that's hollow, so it's empty. In this case, it's filled with a silicate. So I show you the zoom image, show you the detail of that particular the structure of that globule, and then the bottom is a false color image showing you the different elemental compositions. So silicon is in green, oxygen in blue, and carbon in red. So you can clearly see that the hotspot is carbon. It's composed of carbon, and then the inside, the particle in the middle, so that fill the bubble, it's composed of oxygen. So it's oxygen-rich material, likely the silicate of oxide. And so what we can retrace, so combining both the microstructure that we see, so those nanoglobules of material combined with its isotopic composition, we can retrace where it formed. And so basically what we found is that it's consistent with irradiation of ices on the surface of grains. So similar to what you see here is basically you had ice grain, you had a silicate grain, so literally like a piece of rock like you would imagine on the Earth that was covered with different type of ices. And so it's not just ice as you see like water ice, it's basically ice composed of different compounds. So carbon monoxide, so different actual molecule, methanol, so all different carbon-based compounds. And then through irradiation, so we call cosmic rays, so it's really high energy radiation in the other really cold region environment. So when we think about the diagram where I show you the snow line, it's those really far region in the solar system. So really far in the protoplanetary disk, or even outside of those, so in those interstellar medium or like those molecular clouds that I mentioned. So in those really cold region, you can have those reaction happening where the high energy radiation will lead to transformation of those carbon-based compound into much more complex organic compounds that basically forming amino acid and similar compounds that we actually found now in meteorite. And so by just using the isotopic composition and comparing them to those molecular clouds, we see that they have similar nitrogen isotopic composition that basically shows that they most likely originated from those regions. So one of the things that we are working on is trying to really retrace the history of those grains from those organics, from their original formation in the interstellar molecular cloud or really other part of the solar system to their incorporation into asteroids and then their delivery to the Earth. But one thing that's missing to the study of meteorites is when we get a meteorite, we don't necessarily, when we find them on the surface of the Earth, you don't know where it actually come from. So we think those meteorites come from asteroids. but we don't know from which particular asteroid. And when you look at the asteroid belt, there is millions of asteroids in the asteroid belt. So it's very difficult to pinpoint. We have only a very few meteorites in our collection for which we actually have known asteroids, parent body asteroids from which we think that meteorites actually originated from. So it's basically, if you think about a riverbed or like a river, it's like if you would try to basically pick a random rock in the middle of a river and try to understand where that rock actually originated from after its all its life throughout the river and traveling different areas. So it's basically it makes it very difficult to try to retrace its own origin. So that basically shows that there is a really value in terms of knowing the geological context, so like the actual origin from which a given sample comes from. And that's lead me to the reason why NASA has started this OSIRIS-REx mission for studying pieces of an asteroid. So the OSIRIS-REx referred to as this acronym: Origin, Spectral Interpretation, Resources Identification, Security, Regolith, Explorer. And so it was a mission that was launched in September 8, 2016, and it went to study the asteroids called Bennu. And the reason for it is that if you think about the asteroid belt, there is millions of asteroids in the asteroid belt. But then if we look at the one that's the closest to us, those near us asteroids, so asteroids that actually cross the Earth's orbit, could actually cross the Earth's orbit. So they left the asteroid belt and now are in orbit between the Earth and Mars, and are basically close enough that they would likely intercept the orbit of the Earth. And that's what some of those are called those hazardous asteroids, because they have a potential to actually hit the Earth. And so that if you think about, Rachel mentioned it in her talk, if you think about the impact crater, so meteorite crater here in Arizona, you can see that the actual pieces of asteroid actually impact the Earth throughout the Earth's history. But then among those over 20,000 near-Earth asteroids, only about 192 have optimal orbits that for sample return. And what we mean by that is that it was basically convenient for us to send a spacecraft and actually reach that asteroid with using as little energy as possible. So it was basically in a good position for us to actually reach it in a reasonable time. And then the key scientific issue was that it has a small diameter, so it was perfect for actually collecting sample from the surface of the asteroid. And more importantly for us was that it was a carbon-rich asteroid. And what we mean by carbon-rich was those really dark asteroids that must have originated from really far in the solar system. So basically in those region really like close to the comet forming region. So in the really other part of the solar system, and really rich in carbon, really rich in water-bearing components. So there's a lot of water, at least that we thought. And so and the reason we know all those things is basically by spectroscopy. So we compare the spectral feature of the asteroid with meteorite, and we see that it's very similar to what we found. The spectral features are very similar to what we found in those really carbon-rich and water-rich meteorite that we call carbonaceous chondrites. And so among those 5 carbon-rich asteroids that were available for investigation, then Bennu was selected. And if you heard a few weeks ago, there was also a Japanese mission, Haenecour 2, that went to collect from another carbon-rich asteroid Ryugu, and the sample actually just landed this past December. So they successfully reached the sample, and you might have seen some of the picture of those exciting, really dark material that were collected in the sample. So the observation from the Earth gave us some idea of the size and the surface of Bennu. And so here I show you an actual shape model based on radar data from the ground, so telescopic data that were done before the mission was actually launched. It was in 2013. So you can see the shape model is basically about 1,600 feet in diameters. It was thought to be really, really smooth in surface. So it was supposed to be, they even refer to as like sand-like surface. So it was thought to be really fine-grained, sand-like, so like a beach on the surface of the asteroid. One thing I forgot to mention on my previous slide was, while the mission launched in September 8, 2016, he only actually reached the asteroid in December 3rd, 2018. So it took just over 2 years to actually reach the asteroid through different maneuvers throughout the solar system, trying to use as much the Earth's gravity to save as much energy as possible. So if you compare the size of that particular asteroid, and you can see that it's basically roughly the size of what you see the Empire State Building is slightly smaller than the Eiffel Tower. So it's relatively large asteroids. And interestingly, as I mentioned, we thought that it was really smooth surface. However, when the spacecraft actually arrived in 2018, it started this about 2 years campaign where it actually imaged the surface of the asteroid and tried to get as much data on the surface to be able to select a place to actually collect samples. But the surprise was when we received the first image of the surface, is that the surface was not actually a smooth sand-based like surface. It was actually really rocky and rough surface. So here you can see the surface of asteroid Bennu rotating. So you can see the 360 overview of the surface. It's very rocky. It's nothing like you would imagine at a beach. There is really, really large boulder on the surface. Some of those boulders are almost the size of a car, so to give you some idea of the scale. So it's really nothing smooth, and so it was really puzzling, because then how it complicated everything in the sense of like, where can you actually safely have the spacecraft come down, touch the surface, collect sample without actually risking that the surface actually hit one of those boulders. So that basically led the mission to start a really detailed campaign of the surface to try to locate potential area where there is enough fine-grained material and also no really large boulders, so it will be safe for the spacecraft to actually touch the surface. But as you remember, one of the key elements of the mission was the fact that it's this dark carbon-rich asteroids. And so one of the key scientific objectives and one of the work that I'm going to do on the sample is studying those carbon-rich and volatile-rich materials. So basically then the mission also, in addition to just map the surface, use spectroscopy to try to get information about the surface mineralogy or composition. And one of the key discovery was that the surface of Bennu has a lot of really water-rich areas. So when we say by water-rich, we don't mean necessarily like liquid water, but we mean water-rich minerals. So water that's actually trapped in the structure of minerals. And you can see here, this is a map of the surface of Bennu that basically mapped this particular band feature in the spectra of Bennu. So it's a 2.74 micron band that basically relate to those what we call phyllosilicate, which is water-bearing minerals. You can see that the more blue, the darker blue the area, the more enriched in water it is. And so to see that while there is area where there is not that much water, there is a lot of area on the surface of Bennu that actually show relatively high concentration of water. But one of the other things in addition of water that I'm really interested in is organics. And one of the really nice surprise is that there is a lot of carbon-rich or organic-rich region on the surface of Bennu. And so here, and it's also using spectroscopy. So you can see here it's using a different region in the spectrum of Bennu. So it's a 3.2 to 3.6 micron feature. And so here the color is a blue, white and blue is like lower abundance of organics, and red is much higher abundance of organics, showing you that there is those I would call it those hotspot region, or like really localized region where there is a really high abundances of organics on the surface of Bennu. So those initial imaging basically provided us really exciting information that Bennu is actually water and organic rich, which is what we would expect, what we were expected, but confirmed that it will be a perfect asteroid to actually study the origin of organics. So through those 2 years survey, they basically were able to locate 4 different sites and then pound down to one particular site. You might have heard in the news. The name of the site was called Nightingale. And so here I show you the highest resolution image of the site that were acquired by the spacecraft on the right side. And I showed a comparison of a car to scale to show you give you some idea of the scale that particular landing site compared to. And then the image on the lower left corner show you that the spacecraft going down to the surface compared to a general parking spot. So if you imagine a parking spot at a grocery store, that give you an idea of the scale of how the spacecraft will actually land on the surface, collect sample, and then go down. So they won't actually stay on the surface. I'm going to show you in the video in a second. It's what we call a touchdown. So it just touch the surface, stay just for a few seconds, and then back out and leave the asteroid to go back in orbit. And so this site was selected for different reasons. First, because of the composition of the surface, so it's water and organic rich, but also because it's safe for the spacecraft. So one of the key factors that just making sure that it's actually a really safe region where the spacecraft wouldn't actually risk to hit the asteroids or hit any boulders. Here I show you it's a 3D image, so you can see it's a short video showing you the landing site. So it was before the sample was collected. Show you that it's in the middle. It's very fine-grained material. So the spacecraft was supposed to. The goal is for the spacecraft to actually collect sample straight in the middle of that really fine-grained region. So here you can see the 3D flyby that basically was put together to show you some idea of the actual topography. So it's a small dip in the surface that basically collected a lot of fine-grained material. And so then in October 20th last year, they actually NASA did the touch and go. So it's what we call TAGSAM. It's a touch and go sample acquisition mechanism. And the way it works is basically that the spacecraft actually does a lot of maneuvers to progressively come down to the surface, and then really come vertically down to the surface, then touch the surface, blow up nitrogen gas to make material fly around, and then collect material into those collectors surrounding the head of the TAGSAM. And then after about just 5 to 10 seconds, back out and go back in orbit to try to be safe back away from the asteroids. And so all that process lasted, that final process on the asteroid lasted, as I mentioned, it basically lasted maybe 10 seconds or so on the surface of the asteroid, but the whole process took less than a few minutes to actually come down progressively and then back out. And so now the spacecraft is really far back out from the asteroid. So now it's really back out. But I'm going to show you so this was an animation put together before the actual tag event. But we do have there is a series of cameras that actually can visualize the actual TAGSAM head. So it's the circular head that basically touches the surface during the event. So it gives you some idea. It's difficult to actually see because it's so dark that you don't actually see the surface, but it gives you an idea of how material was actually blown away as the nitrogen was blown to push material into the collector. And so here is the image from the actual tag event. So those are actual collection of imaging acquired during the tag. So you see the head going down. Then it blow material and then come back in orbit. And you see the cloud of material all around the head that basically blow material. Then it went back far in space, and there was 2 key events that were planned in the next 5 days after the tag event. So in late October, one of the plans was to extend the arm out in space again and turn the collector to face the camera in space so we could actually see the head and see if we can see any of the material collected in the head. However, what you're going to see is that one issue actually happened is that as they were moving the head, they saw that a lot of particles were exiting the collector, so meaning that actual samples were leaking out of the head as the arm was moving. So just the motion in the kinetic energy from the moving of the arm led to leaking of sample. And we think the reason for it I'm going to show you in the next slide. With the reason for it is because we think that it collected so much material that it actually overfilled the collector. And so there is so much material that the flap that's supposed to close the collector are actually partially open. So that's why some material can actually leak. And so here on the left side, you can see the collector head before the tag event. So it showed that you can see the light. You can clearly see on the edge that there is no material inside of the head. And then on the right side, show you after the tag event, you can see now it's very dark on the edge. So you can see it's completely packed with material because there is no light that can actually go through. So we basically know that there is a tons of material. And the key objective of the mission was to collect at least 60 grams. So to give you some idea, 60 grams is basically a typical chocolate bar relatively. So to give you some size estimate. And based just on the visual inspection, so looking in detail at the rocks or the material, we can see on the edge of that particular image, you can see on the right, there is, and knowing the general density that we expect from the sample, knowing from meteorite, we basically estimate that we have at least 400 grams of sample in the collector, but up to 2 kilograms of sample. So 2 kilograms is basically from test experiment made on the Earth with test material. We think that we can actually pack as much as 2 kilograms inside of the collector in the head. So, and 2 kilograms would be on the order of basically a pack of flowers. So that gives you some idea of like the different size of samples. So basically, we think we collected up to the size of a general pack of all-purpose flower inside of the collector. And so because the samples were leaking, they couldn't do the second test that they wanted to make, which was measuring the sample mass. And the way they do it is by just using the angular momentum. So the idea was to put the arm out in space, away from the spacecraft, and then spin the spacecraft relatively fast to basically compare to the same experiment done before the tag, and so see what's the change in angular momentum that basically gave us some estimate of how much sample is actually in the collector. However, the NASA decided and the mission decided not to do it because every time you move the arm and you will rotate the spacecraft, you would actually lose sample. And so what they decided to do is basically just because you could visually see it's very likely there is way more than those 60-gram base sample mass requirement, that they will just store the head directly into the return capsule and seal it so it's safe inside the capsule, and we are sure that we are not losing any more sample. And so that's what happened just a few days after the tag event. The arm went into the return capsule, so you can see here, it's an actual image video that was taken as it was happening. So it's just a series of images. There is a camera on the side. It's a true colors, so showing you how the sample head, and you can see there is still a few particles flying out of the collector as it was fixed, but now it's basically sealed, and so the capsule has been closed. So now all the material is actually sealed in this capsule and kept safe until the spacecraft can actually return to the Earth. But one of the key interesting things is that the samples are not actually going to come directly. So while the tag event actually happened just a few months ago, the spacecraft is going to stay around Bennu until May. So it's going to do one last imaging to try to image the site where it collected sample, and then fly back to the Earth after this coming May, and it will land on the Earth on September 24th, 2023 in the Utah desert. And so here it's just a general animation of how the process will come. So the spacecraft is going to release the capsule. The capsule is going to enter the atmosphere. You can see it's going to be really warm, but the sample are kept cool inside of the capsule. When it comes close enough to the surface, it will release parachutes that will basically slow it down so it can safely land into the Utah desert. And then the capsule will be collected by NASA and returned to the NASA Johnson Space Center in Houston, where the capsule will be safely open in a lab. So here just an animation of how it will look. So this is the capsule opening, and then the collector head, and the sample, to show you how the samples are in the collector head. So it's just an animation showing you how it will likely look like. So the idea for us is that there probably even more samples than you can see here, because we think that the collecting area is actually packed with samples. So we think that we will have a lot of sample in the collector, and because there probably will be dust everywhere, so that's why they will open it in a clean room, what we call a clean room. So it's a very clean environment where they can actually safely open the sample without having any contamination. And so what we are doing in the meantime is that we are getting ready for it. And so here at the University of Arizona, and for the team all around the world, we're getting all the facility and instrument ready to make sure that we have all the technique and sample preparation technique ready for the arrival of the sample. So to go all the way from the bulk sample on the surface to the sample in the taxam, so in the collector. So you can see here it's an image from one of the tests that were done with some we call it asteroid analogs. So it's basically some terrestrial material that's analog to what we think the surface of the asteroid was made of, and then preparing a thin section, so really thin slice of sample that we can actually study in the lab the same way that I explained to you at the beginning. So using those in situ techniques to actually look for organics and study their composition in detail in the lab. So I will leave you with this last slide where here at U of A we use meteorites that we think are analog to asteroid Bennu to study their mineralogy, microstructure, composition, and organics in those samples, using a large variety of techniques to try to get ready for when the Bennu sample actually arrive. And so I hope in this brief presentation, I hope I show you that the analysis of the return sample will help us not only characterize asteroid Bennu and understand how it formed and evolved, so retracing the history of asteroid Bennu, but it will also help us constrain bioessential element and how bioessential elements were delivered to the Earth and were they delivered by asteroids. And for that, I'm going to stop here, and I'm happy to answer any question. Thank you.
Thank you. We did have a few questions, so I'll kind of go back to the top of what was typed in. Tina asked, was the force used to sample based on predicted density of the asteroid? Since more sample was collectible and expected, that impacted such a prediction?
Yeah, so what they did test in the lab in like asteroid-like environments and like zero gravity to try to basically test how the system will work and how much nitrogen do you need to actually blow material and make sure that it could actually flow away. So all were calibrated in the lab before, well before the launch of the mission.
Okay, thank you.
And one thing I didn't mention is that they actually could have do 3 tag events. So there was enough there were 3 bottles of nitrogen, so they could have actually do 2 more touchdown if we didn't think we had enough sample, but because the collector was so overfilled with sample that we didn't use the other 2 bottles of nitrogen.
Okay, thank you. And then we did get this from 2 different people. So what is the discussion for mining asteroids in the near future? So is that something that's being discussed as a mission for, yeah.
So that's one of the things. Is similar to the idea of like mining the moon, except that the asteroids are much further, but it's the same idea. So basically part of the mission was to image key elements. So I focus in my talk about water and organics because that's what my research is focused on, but they also look for a lot of characteristics of different minerals that they were looking for. So a lot of study will be done also on other key elements that could be potentially used for mining in the future. But that's not the main objective of the mission. Is mostly in a research side of understanding the origin of our solar system, but with the side project of potential mining in the future.
Okay. And then Larry would like to know, can you explain plans for the return sample? Will some be archived or shared with other labs too?
That's a really good question. So the way it works, so the plan so far, so as I mentioned, we had 60 grams. So within those 16 grams, only 15 grams of those 60 grams will be used for sample analysis. So that's the only sample that NASA will allocate to researchers for actual analysis in the lab right now. All the rest of the sample, except for a small fraction that will be shared with international collaborators. So there is collaboration with, for example, Canada and Japan. So they will get a really small fraction of sample as well for analysis. But but the large majority, so like 75% of the sample will be actually stored for long-term archiving because the idea of preserving sample is that technology evolve and analytical techniques evolve through the years. And so the NASA want to ensure that we preserve samples for future investigation in the long term. So when we have more extended capabilities, so we can actually do more samples. So if you think about it as I know there was a talk a few days ago also in this program where it was about Apollo samples. So one of the key things for Apollo, for example, that they preserve a fraction of samples that were preserved for those past decades. And then recently they opened a new set of samples that can be studied now with all the updated state-of-the-art technology that we have to try to get even more information from those samples.
Thank you. And then there was some chat going on about still the mining and the resources, and is it worth it for the money because they're so far away? But then Rachel points out that there's millions of them. So kind of unlimited resource, if you will, except that they take a long time to get to. But yeah, it's kind of an interesting conversation going on.
Yeah, and it also depends on what element we are mining. So some element might be worth it because they are so valuable that it might be worth the investment to go there. And NASA had a plan a few years ago that about trapping an asteroid and bringing it back in close orbit, so it's easier for us to actually send astronauts to go directly mine or study the asteroid. So
wow.
So there is different plans that have been through the years. I think that particular mission never went through, but there is plans for like ways of we could actually brought back asteroid closer to the Earth in like safe orbit that will allow us to be able to reach it without having to go so far out.
That's crazy. And let's see. So we got some questions too about living on an asteroid. So is that possible? And then someone else, Carol, is asking, is there enough water in asteroids to create the oceans?
No, so there is very little water. So when I say it's water rich, it's really relative. So the water is actually, there is no liquid water. There is the water is trapped in mineral phases. So there is no free water. So there is no way for us to actually survive. And then asteroid, the most important for us is that asteroid don't have any atmosphere. So there is actually no way for us to actually really breathe or live freely on the surface of an asteroid in any way. And it would be very cold because they are so far from the sun. That would be very cold and very dark. So it wouldn't be really appropriate for us to live on an asteroid.
Okay. And I'm just kind of looking around to see. Yes, Laura Beth says perpetual winter. No, thank you.
Exactly. Also, you have to imagine, it's a very rough surface that basically there is collision that happen between asteroids. There is boulder that moves on the surface. So it's not a really necessarily friendly on my environment. Those asteroids, the density of the surface is very low. So it probably be very difficult to build anything on the surface. It wouldn't be doable. So there is no reason for us to even consider it at this point.
And then for my own question for Bennu was how do you pick out an asteroid to go study out of all of them that are out there?
So that's what I was.
I know you were explaining that, but I think I need like maybe one more summary about. I know.
Yeah. So there is different aspect of why. So the key one is, can we reach it more efficiently? So basically, can we send a spacecraft and it can use like Earth's gravity assist to reach it, so we don't have to use so much fuel or so much energy to reach it. So that's that already limit which asteroid we can actually reach by just the capabilities. So is it even feasible in a reasonable time to actually reach it? And then the other aspect is scientifically, which one are interesting. And so that's what Bennu was selected, is because it was close, it was relatively easy to reach, but it was also one of those dark asteroids rich in water and organics. So it basically was one of those perfect fit. And so one thing I didn't mention is like, now that as soon as the sample will be delivered, so the spacecraft is actually going to stay in space, and so just the capsule is going to return. So there is actually discussion right now for an extended mission. So what we mean by that is using the spacecraft for additional research. And so one of the plans is to send the spacecraft back in space and go study another asteroid. So it wouldn't be able to collect any sample because there is no capsule to actually return the sample, but there is all the cameras and instrument on board the spacecraft that will allow us to study another asteroid. So there is plan now to go to another near Earth asteroid that have been in the news recently. It's because it's a potentially hazardous asteroid. It's called Apophis. So there is plan for the spacecraft to go back in space and go study that asteroid because it's a potentially dangerous asteroid that might hit the Earth in the next century or so.
Okay. Thank you. Lucas says, great talk, Pierre. Listen, I really enjoyed it. I really enjoyed it too. This is fascinating.
Oh, thank you.
Science fiction in real life. And
Yes.
Rachel says, are any of the samples going to be preserved for decades later?
Yes, so 75% of the sample will actually be stored. As soon as we open the capsule, they're actually going to save 75% of the sample will be sent to another facility, so they don't stay in Houston. They go to this facility in White Sand. It's in New Mexico. It's basically just a huge vault that basically where we all the preserved collection are stored for decades or to come. So basically just archived. So the large majority of sample will actually be archived. So
okay.
So for the sample analysis, we only have a really, really tiny fraction.
It's just so fascinating. Oh my goodness. Well, I really enjoyed your talk and your presentation, Pierre. Thank you so much for joining us for Astronomy Day.
Thank you very much.
Thank you, Pierre. It was great.
Thank you, Rachel.
Thank you for coming.
Yes, and if it's all right, I would like to share my last slide. So I might, yes.
Okay. Stop sharing.
Thank you. Yes, and I'll show our last slide of the day for Astronomy Days. And it is indeed Sunday, everyone. I'm back on board here. Thanks again for joining us. We're so glad that you could participate. I've been joking around, but serious about commemorating this virtual time here and ordering your Astronomy Days t-shirt. So you can join us in supporting the museum and remembering this experience. And thanks again for attending, everybody. Have a great rest of your Sunday. Have a great rest of your week. Bye, everyone. Thank you.
Thank you.